Okay, in section 3 we're going to look at how the graphs of f and its first and second derivatives are related. Now in this first problem they're giving us a graph of f prime. They want us to analyze this thinking about what the original function would have been, and we're going to use information about this graph to think about the second derivative and again what that tells us about the original function. Now the first question asks about intervals where f is increasing. So we're just looking at this graph specifically. I'm going to move to this page. And if we're looking where f is increasing, we're going to first look for our zeros of f, which are happening at -2, 1, and 4. And we'll also probably consider our endpoint over here, -4. But we are getting zeros at -2, 1, and 4. And we want to think about what's happening between them. Now, since these are all positive, and then from 1 to 4 we're negative, that's telling us that we're increasing everywhere from from -4 to 1. Now this does tell us something about our original function f. The question is asking, where are we increasing? Now we might want to say that we're starting at -4 and then we reach a 0 here. Now we don't want to write it like going to -2 and then have an open dot and then continuing, because we continue to increase from -2 to 1, but we are still increasing really here. Even though we have a shelf point to 0, we're still increasing because every point as we move from left to right is a little bit higher than the previous point. So instead we're just going to say that we're increasing from -4 to 1. The next question asks, what intervals is the graph of f concave up? Now looking at concavity, the second derivative when it's positive means we're concave up, negative we're concave down. Or this graph, consider its derivative. So if we look at the graph of the derivative and we think about its derivative, okay, first of all, horizontal tangents are going to be zeros for the derivative of this. The derivative of this is the second derivative. So these horizontal tangents are having a -2, 0, and 3. We can also look at this graph and notice that f prime is decreasing. It's negative, which means we're going down. Then we're going up from -2 to 0. From 0 to 3 we're decreasing, and then from 3 to 4 we're going up. So since this is our second derivative, it tells us about the concavity of our original function f. The negative means we're concave down, the positive means we're concave up, down, and then up again. So on what intervals is the graph concave up? Again, this is where we're positive, so from -2 to 0, from 3 to 4. The next question asks about local extrema. So if we're looking for a local extrema, we're looking for places where f prime has a change in sign. So our changes in sign for f prime are happening here at 1, but we also need to consider our endpoints of this, which are happening at -4 and 4. Now since we are increasing here, going up from there, that means that's going to be a minimum. Here we're going up and then down, which means we have a maximum. And then at the other part we're going down to that, telling us that this is a minimum. So we'll have local extrema, we'll have our minimums, x equals -4 and 4, and a max at x equals 1. Okay, the next question asks about the x-coordinates of inflection points. Again, inflection points come from our second derivative. These are going to be happening where we have a change in sign. And our changes in sign are happening at each of these points, -2, 0, and 3. And so each of those will be an inflection point. Now for the final question asking us to sketch a possible graph on this interval, I'm going to put this together in a different way. Now in the book they put this sign chart, they join these two charts together into something look like this. And I want to simplify it just a little bit more. If we look at everything, basically taking all of our critical points, here, -2, 1, and then our endpoints, we can look at what the first derivative is doing, where we were positive, positive, and then negative. And then we're also going to look at these zeros for our second derivative. In this case, they were all inflection points, where we had negative, positive, negative, and positive. Putting all that together, these are telling us that we're concave down, concave up, concave down, concave up, and the f prime is telling us which direction we're going. We're going up, we're going up, and then we're going down. Now they didn't give us a starting point, so I'm just going to start in a random spot here. I'm going to start down here because we're going up after that. So we know first of all that we're going up until we get to -2, and we're concave down. And then at 2, we reach a horizontal tangent line. We continue to go up, but we are now concave up. So we're curving up. And it's when we reach 0 here that we're no longer concave up. We are still increasing, we're still going up, but now we're curving back down again. Now looking at our first derivative, we're getting a 0, which is telling us we have another horizontal tangent line here. And we're going to begin to go down here. Notice we're still curving down. We still have a negative second derivative, so we're curving down until we get to 3. At 3, this is our second derivative, so it's a change in concavity. We're now curving up. We're still going down, but here at 4, we're going to level out and have a horizontal tangent line again. But what's important again is the inflection points, where we change in concavity, and whether we're going up or down. Next, I want to point out that just because we get a second derivative of 0, we're not guaranteed to have an inflection point. It's not just having f double prime equal to 0. We do need to have a sign change. For example, in this one, notice we were concave up, so f double prime would have a positive on this side and positive on this side. So it can't be an inflection point if there's no sign change. Another note is it doesn't have to be where f double prime is equal to 0, because it could be where f double prime does not exist, but only if the original function has a vertical tangent line here. So you'll notice with this one, if I take the derivative, I'm going to get an x in the denominator, and so the zeros are going to give me it does not exist, and that's because it's a vertical tangent line. And then for the same reason, my second derivative will also have a 0 in the denominator. But what we need to do is go back to the graph and decide if that's a vertical tangent line, which we would know because it's continuous and it's not a corner or a cusp.